This conference will now be recorded.
Okay, Kenneth, thank you. It's all yours.
Okay, so hi everyone, my name is Kenneth Ma from Xilinx, and today I'm going to give you a OpenHBI workgroup status update. This will be a short one because OpenHBI is structured as a closed workgroup, and then we will be updating to the ODSA main group and sometimes to the OCP event once in a while, but then those are only from a work group, from a spec readiness and some of the high level features perspective, because the spec will only be published when it is ready to become a OCP specification. But at the meantime, we can do some quick highlight of where we are so that the ODSA group will understand the status of the work stream. So let me start sharing. Forget the button again. Here. So I hope you can see my screen now. So I will start off with the workgroup status, and then with some of the key features and characteristics, and discuss some of the figure of merit, and then other characteristics of the spec of the OpenHBI interface. Many of you actually have seen bulk of this presentation already, and but that is about 6 months ago. So this is including some update, which is some of the key update of the last few months. And I will get started right now. So first, workgroup kicked off about 1 year ago, plus a little bit, this February 2020. We are very focused on the high-performance chiplet-based architecture, and we intended to deliver the best-in-class figure of merit. And we start off by leveraging the HBM and HBM3 specifically for the I/O features and ecosystem. And the intent is ultimately to build the interoperable third-party chiplet ecosystem, just like the ODSA intended to do. Our members are comprised of the leaders in the IP world, the accelerators, SoC, FPGA, systems and test. And I'm glad to announce that from the last time, we actually have ARM and Teradyne join the work groups as new members. So we have 7 members right now, and so the list is here. So ARM, Cadence, Google, Sci5, Synopsys, Teradyne, and Xilinx. And thanks to the various referral, especially Baptiste referral, and then the other channels, we have ongoing engagement with potential users, adopters in automotive world, the cloud, hyperscalers, 5G networking on their, either the requirements and some of the target characteristics. Good news is that the top 3 requirements that come back is always the latency, bandwidth density, and the efficient picojoule per bit. And the bandwidth per millimeter perspective, they are requesting, almost everyone is looking for 1.5 terabit per millimeter or higher. And then some of them is even higher than 2 terabit per millimeter. So that would be something that OpenHBI is targeting. The structure of the work group is that we originally start off with a core group to drive the overall architecture, the interoperability, the clocking, configuration, and testing aspect. And we formed a new I/O electrical subgroup several months ago to focus on the channel definitions, I/O electricals, the BER, and then the clock definitions. I myself is chairing the core group with the Andy Her from Google is the vice chair of the group. And then Andy is also the chair of the I/O electrical subgroup. I don't know whether Andy actually can make it today or not because he has a conflict until later, but yeah, he is the vice chair. And again, because we leverage the JEDEC HBM, so it's inevitable that we have to talk about some of the JEDEC HBM spec characteristics during the proposal phase. So that's why we require the JEDEC membership and have to make it closed, and also involve some of the HBM related potential IPs, and then the members want to be sensitive about. So that's why we also need to have execute a contribution license agreement together with the OCP community membership, which I believe everyone here is. So we structure it as a closed work group in order to participate. So that's how we structure. So the next slide, we will focus on some of the high-level key characteristics and why OpenHBI is special. So OpenHBI, again, we are focused on very high terabit per second chip-to-chip interconnect. Ultimately, we may consider some, hopefully broader maybe lower cost use cases, but in the beginning, we see there's enough opportunities of the high terabit, C2C interconnects. And we are focusing on the like silicon interposer, wafer level fan out, or similar advanced packaging technologies. Like but unlike the HBM, we leverage the HBM, we call the D word or data word, as a building block. However, instead of a bidirectional like a memory operations, we construct them as a symmetric multi-channel interface. And some people call it dual simplex, some people call it unidirectional, and then either way, we make the as a transport layer, it is symmetric between one side versus the other side. We don't actually differentiate the master and the slave, for example, but then that aspect can be differentiated when you start mapping the protocol to it. Just for example, if you want to map a PCI host end versus a PCI device, to the OpenHBI interface, then one side becomes the host side, the other one will becomes the endpoint. But from a transport interface perspective, they are symmetrical and they are multi-channel, and those are a number of the channels, the grouping, they are all composable and they are scalable. And each of the D word as a building block, it can carry up to 42 data signal. When I said up to, is that typically some of the signals are being used for other things like you have to know the framing, you have to know which one is the first beat of the burst. So those kind of informations may consume one or two signals depending on the mode. And the other signals like a DBI, which is standard inside the HBMD word, those are optional and can be used. And then when you use them, you decrease the number of the data signals, and those are controllable by modes. One of the very interesting characteristic of the D word and the OpenHBI is that we allow a configurable TX and the RX personality at boot time, or you can dynamically configure them at the runtime. I will go through a little bit more about the use case later on, but then just please remember this is a configurable, when you're operating it or at the boot. Electrically, it is an optimized derivative of the HBM electrical, and it is electrically interoperable with enhanced PPA and FOMs. For example, we are boosting it to 8 gig trans per second by leveraging the shorter reach. Typically, the HBM is a longer reach because the bit frame is in the middle of the package, but for OpenHBI, it will be edge to edge. So the spec will be up to 3 millimeter, but then nominally it will be less than 2, unless you have a lot of misalignment of jogs. And then the figure of merit on the picojoule per bit is lower correspondingly by optimizing the drive. Bandwidth density, in the previous presentation, you will see.
Quick question, if you don't mind.
Uh-huh.
The 0.4 picobit per joule, is that for terminated or unterminated bus?
Unterminated.
Okay.
And yeah, thanks for your reminder. Actually, this 0.4 is from the entering the PHY on the TX side through the IO, through the channel to leave the PHY on the RX side. So it is inclusive of the PHY layer on each side and is a transmit of a 1-bit energy. So that's the definition. I believe is consistent for all the ODSA PHY layers. And we estimated that this is based on the non-DBI, and then with DBI, technically it should be a little bit improvement. But so this is not including the DBI effect.
Okay, thank you.
Thank you. So from a bandwidth density perspective, in the past, you may have seen some version of the presentation saying that it is about 1.7 terabit, and then we now have a range. The reason is that back then the spec team has not fully defined in terms of our bump map, the height of the beach front, etc. Now the team has decided that there will be a range, and so we will have a range as well. And I will give more details in the next slide. And the what BR target is based on some of the UI base and the jitter analysis, etc. We are targeting the 1D minus 25, which is achievable according to the IO electrical expert team. So it's a multi-layer architectures. We're focusing on the transport layer and then leave the adaptation and the protocol layers above it. And then so we can allow the flexible mapping. For example, if you want to map the PCI Express, C6, CXL, or other protocols, AXI, is implementation specific using through the adaptation layers, or the protocol layer, if they have a knowledge about the transport, they can directly map to it to reduce the so-called layering. We can also go through the ODSA link layer, which is, I believe, is still in definitions. Finally, the one key characteristics about the OpenHBI is that it is allowing, I mean, what's the reason of leveraging HBM? I mean, other than this provenness, is that it allows a implementation specific dual mode, OpenHBI for chiplet and HBM3 for memory mode. So the benefit of this is that if you have a product that you want to have a flexibility to, I want to have some I/O or some protocols or some other features that you want to use a chiplet. However, in the other mode where you don't need those features or you want to be configurable, and then you want to support memory intensive, compute intensive applications, you can then hook it up to the HBM memory. However, typically these two are very different from a construct and from an operation standpoint. So if you use any other interface other than the HBM-based D-word structure, you cannot do that. So if you do not use the chiplet, you cannot reuse the same beachfront for HBM. So by allowing the supporting the D-word structure, we allow the implementation specific, which is out of scope of the spec, but it allows a dual mode HBM host implementation like shown here. So in one mode, acting as a chiplet, or we call it anchor, you can connect to the other chiplet on the right. On the other mode, you can act like a dual mode host and connecting to actually this one. We just put a HBM memory here to the right. Okay, so
Ken, one question.
Go
Question
ahead.
is, how is it different than a BOW?
In terms of what? It's quite different.
So, I mean, do you expect one chiplet to have one HBM interface and a separate one for BOW, or can they be the same IOs
They are
interchange
not.
between how you configure it?
They are not the same IO. I mean, the BOW, I understand, is using the 0.75 volt IO, basically the core rail kind of, and then the HBM is using the 0.4 volt low swing NGS IO. So they are electrically not the same, and then we are electrically leveraging the specification of JEDEC HBM. So that's the first difference. The second difference is that the structure is very different. The BOW is 16 data wires plus clock and a couple others. We are a 48 signal block, which I will show you in here. So in 2 slides, I will show more.
Ken, I had a question.
Okay.
So say in a scenario, I have an ASIC or an FPGA, and I on the west side I want to connect it to a macro, and on the east side I'm connecting that FPGA or ASIC to an HBM. What you're saying is I don't need a special HBM PHY to talk to the HBM. I can use the same Open HBI PHY to talk on both sides. Is that correct?
Okay. Depending on, we need to fine tune the terminologies.
Okay.
From we separate the IO and the PHY and the logical PHY layers, which I can jump to here.
Okay. So if you were going to cover it later, that's fine. Sorry.
Yeah, no problem. So no problem.
Thanks.
Maybe another quick question, Ken, which is maybe a variance of the two questions that were already asked. Say if you're doing an OpenHBI and you're already an interposer because of OpenHBI, would be any reason where you would want to use BOW, say for example, between
well, for on the same design, the answer would be no. Yeah. But on the different design BOW, I mean, of course, it is at least one of the skills is targeting for the lower cost, the organic substrate. So those
that I understand, but on the same design.
If it's on the same design, well, personally, I don't see the reason, because unless you want to have a anchor SoC that want to support the multiple types of chiplet from an interface perspective. For example, there's nothing to stop you from doing one design to have BOW, AIB, and OpenHBI, but is there any reason for that? I think it's the system, the integrators to decide. But from our perspective, we allows a multi or scalable the C2C interface along the beachfront, meaning that you can have, let's say I give you an example diagram here, which I will jump around. You can have a anchor like this with multiple of them. If you start putting the HBI all along the interface, then you can do, anchor to anchor. You can do like this kind of construct. You can do anchor to chiplet. You can rotate the chiplet around the edges, and then we allow all this to be supported. And I will go through details. But my point is that if you want to put BOW in the interposer mode, or you want to put AIB, if you can, I don't see any reason you cannot. I mean, there's nothing related to the core specification here. So
Sure.
it depends on what you are available, because if you have other chiplets that is available that you want to interface with, I think that's the reason. But if it is all from a future perspective, and then we all have the same classes of the chiplet to support in each interface family, I don't see the reason for that, because you now have to verify multiple interfaces. You have to, from an integrations perspective, they are very different. And the advanced packaging is very unforgiving, right? So you have to be as consistent as possible in your design.
But Kenneth, at the same time, the reach for BOW5 is longer than the open HBI, right? Because this is 2 to 3 millimeter, and that is targeted for 10 millimeter, right?
Again, when you are putting, we started with this one, right? We talk about, we are focused on the supporting this one, advanced packaging technologies. Once you are on the interposer, you are limited by the maximum reticle sizes, right? And then the advanced technology can go 2x, whatever, or way beyond. Not way beyond 2x. I cannot talk about details, but still you are limited. So that means whatever you do, you are not like the on organic substrate, where you can have a 10 or 20 millimeter.
No. Fair enough. Fair enough.
Yep. Okay, so let's talk about this. This is should be interesting. So OpenHBI from a spec perspective, originally we definitely understand that we want to have a common pitch and a height, so that we can get a zero misalignment. And however, again, because of the technology choices available, and we, as a spec team, we decided that the Y pitch, which is the pitch bump to bump pitch along the die edge, we define a range, and correspondingly the DWAT height will also have a range. And we don't anticipate this will cause any problem in the beginning of the life cycles, because we don't think that two chiplet from A side and B side, they will automatically be interoperable in the beginning of the life. We anticipate there will be couple generations of chiplet that people have to co-design and owns both sides. And then if you choose 55 micron on one side, you have to choose 55 micron on the other side, and you have to know how to align the anchor and the chiplet from the interface perspective. Just like all the other spec, they don't actually define where the bit front is relative to your die edge, to your the rest of the circuit. And if you imagine you on the anchor is on one edge that is aligned incorrectly with the chiplet on the other, the bit front on the chiplet side, the things will be kind of like mechanically pretty odd. I don't have a diagram to show, but what I'm saying is that the co-design is important in the beginning. Once that phase is passed, then whether the industry will normalize itself, or we can add the more constraint to help the interoperability. So those are originally planned, but due to the advanced packaging technologies are still evolving, so we are leaving it as a short range here. But because there's a range, so we separated the min-max case in these two columns. This is just a geometric relationships, where this one is kind of like the HBM2 numbers, if you remember, 55 for X and for Y and the X minimum pitch, and X is 96. Equivalently, if you choose to have advanced, let's say down to 40 micron, and geometrically this X pitch will become 70. And then the remaining numbers are all derived from it based on the virtual bump map. The virtual bump map will be in the next slide here. So based on that, we derived all these numbers. 0.4s were unterminated, up to 3 millimeter, typically less than 2. And in fact, the best route you can get down to less than 1.5. 8 gig, which is very achievable at 1D-25. And we only count 40 signals. As I mentioned, we have 42, but then we exclude. Already, we don't count the clock or lane repair signals. Those are excluded from the 42. But we include the framing priority signals that is, to be used in typical case. So that's why we count 40. So if you take the 40 times 8, which is 320 gig per D word, and we have a 32 such D word in a bit front, in this bit front, 32. So when you take 320 gig times 32 D word, you have a 10.24 terabit of the data carrying bandwidth. Okay, not per signals, but just the data carrying signals. Then divided by the bit front, you get these numbers, 1.66 terabit per millimeter. And then if you go 40 micron, then it will be 2.29 terabit per millimeter. And area-wise, it will be corresponding. I mean, we are not sure about where people were landed in the beginning, but then we think that the technology itself is very feasible to allow the 40 micron. But of course, the I/O design, etc., has to be either balanced or not IO limited to achieve this performance. So,
quick question: why do we need to follow the HBM bump pitch here? Is there a particular reason?
Oh, I'm sorry. Can you ask one more time?
This is Halil. I am curious why we copied the bump pitch from the HBM.
Oh no, we don't. We don't copy the HBM bump pitch. We leverage the bump map. So when you set the bump pitch, the HBM3, it is the Y pitch is 110, and then we are using the 55. However, if you look at the reason why they have the 110 on the memory side, they are actually required by the memory vendors for like the larger the digital decap and other things on the memory side. But on the digital or logic devices, if we, I mean, okay, for the anchor and the chiplet, if they are logic processes, we definitely can do, the 55 micron. For the analog mixed signals design or people that want to use older processes, we actually have get some input that they can still use this 55 micron from an IO perspective. But then, of course, they may have some additional requirements outside of this bit front. So my point is that maybe we don't have the diagram in here, but let me verbally explain. When you look at the 55 versus 110, and then this is the virtual bump map, as I explained. If the other side is the HBM memory, which is 110, but you can massage this bump map to be compatible and routing compatible to the HBM memory. I didn't prepare that slides, but if you imagine that, let me just see if I can play with this one. Let's say if you compress this into half from a width perspective. Do this. If you can compress this into like this half, and then but you make them look like the right side. So this is from a bump perspective, they are equivalent to a 110 but narrower bit front because each of them are 55. So, and from a routing perspective, you are having these 6 signals to be sharing a 55 micron channel. And then the other side, the HBM, which is 110, they are 6 deep, but using a 55 micron channel. There will be a minimum, if you want to call it jogs, of a few microns here and there, but then they are all strict routable. Does it make sense to you from a concept standpoint?
Yes, it makes sense.
Okay, so this is how, in fact, while we are here, might as well talk about this, if you guys don't mind. And thanks for all the questions, but then I actually intended to address all of them when I go through, but it's okay. So we call the virtual bomb map target. The reason is that we don't want to have a fixed bomb map after the discussion with all the stakeholders. The reason is that when you actually do the physical design, especially when you do the advanced packaging, there's a lot of considerations that you cannot say, okay, I give you this bomb map and do it. And because the power and the ground rail, for example, people can use different rails. People can use a different power delivery architectures. So we give them a concept that, okay, this is a HBM3 bomb maps. And then if you imagine that you have a chiplet on this side, A, and then you have another chiplet on this side, B, that we are saying that you just need to make sure that your bomb map, your bomb pattern, when you have a multiple layer of the routing resources, I don't care if you actually completely follow or not, but you need to be straight, seamless, no crisscross, and then the trace matched when you route to this virtual target, which is HBM3 based. Then by definition, if you can route to this from A to here, from B to here is straight, you remove this, and then from A to B is straight. So this is to have facilitate the interoperability between the third-party vendors without actually defining a fixed bomb maps. Now, the issues about if one side is 40 micron, the other side 50 micron, the problem remains. So those are the one that requires the co-design. But again, those are not inevitable problems to solve because advanced packaging are very expensive, very complex. We don't want a simple spec like OpenHBI spec to mandate, people's, tens of millions of dollars investment. So this is how the virtual bomb map target is defined, and then it seems to work very well so far. So I hope it explained the questions.
Thank you very much.
Yep, and again, if this one is if you use HBM on the other side instead of chiplet, like I explained, you basically just compress these bomb maps, and then they are also routable. But conceptually, you just have to mentally look at how I draw earlier, and then that becomes a 55 micron times 2, matching to a 110 micron on the HBM side. So those are all being considered when you do the dual mode. But again, dual mode is outside of the spec. We said allowed, but into operation. But so it is considered, but not defined. Okay, so let's finish up this slide. Because of this, we already exceeded the 1.5 nominal requirements that many of the advanced use cases, and then we can exceed the 2 terabit per second per millimeter for some even more advanced requirements in the few years down the road. So we, as a group, we already planned the beyond 1.0, even the 1.0 is not here yet. So it's just like all the other consortiums or standard work groups, we are planning the roadmaps ahead of us, and then we are having substantial FOM advances planned in the next generations. Okay, so back to this bomb map. One more thing is that the standard, the D word has 48 signals. How they construct it is they have 42 signals. They have in the HBM, they have the database inversions, they have other signals, which I don't know is sensitive, confidential or not, but then they have 32 DQs. If we harvest and use all of them as the data carrying signals, because for chiplet mode, it is generic, we don't necessarily need them to be doing DBI, for example. We can have up to 42 signals. And on the, we talk about unidirectional, so on the TX side, they are output, on the RX side, they are input, and they carry data. There are the unique things about HBM is that they have 2 sets of clocks. One is called a WDQS, which we use as a TX clock, and then the other one is the RX, the RDQS, which we use as a RX clock. And then when you configure them as TX, then they are output. When you configure them as RX, they are input. Now you can say, what are they used here? They are not used. And I put an asterisk. This one can have a very interesting characteristics. This is where we can allow the boot time and dynamic configuration. So imagine if you configure during the middle of the operation when you have a hyperscaler or a cloud or other use cases. When you map to different use cases, you may not want to map the constant set of the TX and the RX to depending on the chiplet, depending on the features in the chiplet that you want to enable, depending on how many D word that you group to support a particular protocol. For example, you can imagine if just an example, random examples. If you want to map PCI Express, Gen 6, one use case you want to map by 16, the other one you want to map by 8. You don't want to use the same set of D word and waste half of the bandwidth. So you can dynamically map the unused the D word if you only go by 8 by 4, and then use those for something else. And then of course your chiplet has to be capable of doing that, but then allowing that that they will give you a very dynamic configuration. But not only that, we are only talking about the D-word aggregation and D-word utilizations, but the D-word polarity and we call personality is also configurable. So imagine that you have some workload that you have more write traffic than the read traffic, or storage or other things than the or some design actually is unidirectional. Let's say they are the advanced cameras or the ADC, DAC. Those are all unidirectional traffic that you don't need to be always balanced. So we allow them to be configured dynamically. And when you swap the personalities, the clock itself, unless you make the clock the reverse polarity, which is very difficult from a design at a high data rate, we actually can now reuse the unused pair when you swap the personality. Then those unused pair can help with the dynamic configurations. And because of that, we even allows you to repair the clock. Those are details which I cannot go through, but then from a usage perspective, we can even repair the clock lanes if they are broken, which the HBM memory cannot. So, okay, so this is the high-level layering structures. We only define the PHY and the logical PHY layers and leave the upper layers to be flexibles and mapping, and you can have the optional adaptation layers if you like, or you can have a protocol layer directly to the OpenHBI as a transport. So this blue dotted line is the PHY and logical PHY. The PHY layers, I think everyone is the same. I mean, they have the I/O, they have the clocking, stripping, some gearbox. If your internal data array is, let's say, if your internal logic clock is 1 gigahertz, externally you run at 8 gig, you need to set the gearbox like 8 to 1, just for example. Some calibration training, deskewing, all done here. Lane repair, which is leveraging the HBM style lane repair, and then it's done here. The logical PHY, we need to do some framing and alignment so that you know which one is the beginning and the end of the burst. So when you do 8 to 1, for example, or 4 to 1 serializations, you need to know which one is the bit 1 or bit 4 or bit 1 versus bit 8, depending on your ratios. DBI, standard features. Bit reordering, this is a new feature and this is unique to OpenHBI. Because of this bit reordering features, you can guarantee a strict route on the interposer, even if you are rotated orientation. If you imagine you have originally a straight wire across the anchor and the chiplet, but now one side is rotated. Go to this diagram. If you come from here to this side and they are the same chiplet and you rotated them, then you will be in the rotated orientation. Now, this one I draw I can move them around. So this one, if you do the mirrored on the left and right, then this one will definitely be considered as rotated. Then the wire cannot be straight. And then we have defined the mechanisms and consideration in the spec to allow any combinations of this and rotated. And of course, the same relationship of rotated is on when you go to the top, you can see here. But this one will be no crisscross. And in here you can see, well, what we need to do with one version of the reordering. So people will say, hey, if you restrict the spec to certain rules, then you potentially can make them no reordering required. However, OpenHBI also allows these use cases. If you have a very capable chiplet where you can allow the chiplet to chiplet, then you will be inevitably has to be rotated like this. So, right, and then if you allow the anchor to anchor connections, a simple case would be like this. If you just want to build a 2x2, but if you want to build a more complex, mesh, now this is just a logical diagram. This is limited by the radical size we said earlier. You cannot build this unlimited, but conceptually you can build this, and through the OpenHBI. depending on the construct, and I won't go into the details of our rules, but then if the construct is here, you already have a reverse relationships between these two, and then by having this we call the bit reordering at the logical file layers, we resolve all of those interconnect issues by, and then you don't have to crisscross, you just route it straight, and then also you can mostly the trace matched from a length perspective between the anchor and the chiplet. And one important aspect is that we still support lane repair in all orientation and combinations while doing all of this, bit reordering. So this is
question. Yeah, so the bit ordering, do you do lane reversal or is it the finer granularity of bit reordering?
So well, at the high level, I actually I don't know whether it is still sensitive part of the spec at this point, but basically, if you look at this conceptually, if you rotated this one like this, then you can imagine that this wire from here will be going from here to here. If you connect them just one-on-one, and then vice versa, if you like this. And if you keep drawing it, they literally all the wires they cross each other. Unlike if you are in the same orientation, they will be just straight wire across. So what the bit reordering have to do at this high level, there's a lot of details and nuances, including the clock and how do you deal with the lane repair. Those are very detailed. But then from a signal to signal perspective, you just need to, at the logical level, to make these signals, make this one look like this one here. Does it make sense? So you, in this case, you will, instead of connecting to the other corner, you connect to here. Instead of use a different color, and then instead of you go across, you connect it to here. Then the bit reorder, because at the logic level is very easy to do. So oh, I'm sorry. Yes. So in this case, you basically just reorder the things logically to reverse it back to look like this. Does it make sense?
Yeah, thank you.
Yeah.
Understood.
So
and
this
what
is
what is the violet color bump indicates?
I'm sorry?
The violet color bump you have, right?
Oh, good question. So this one, the in the HBM bump map, the VSS is the so-called VDDQ, and then I believe it's 1.1, and then the VDDQL, which is in the violet, which is a 0.4 volt. We, as I said, we don't. Oh, sorry. Not the VSS. VSS is ground. The VDDQ is 1.1 in HBM, and then the violet is a VDDQL, which is 0.4. Again, for memory. But from the chiplet perspective, all these are only reference only. You can do whatever powering ground bumps, and you can do without it. You can say I don't need any of this, and then I put more ground, more power rails, or you can skip the row depending on your dimension and the design, as long as you control both ends. However, in order to meet the general D-word height requirements, we recommended both from a PDN and from a design compatibility perspective. If you, let's say you do 55 micron and you follow this bump map, that will still match and minimize the misalignment. But if you said no, I control both sides forever, there's no reason that you need to keep all the bump and the power and the ground the same. So you control the whatever as long as you can have both sides work with each other seamlessly. So we give some flexibilities to custom design, but then from a spec perspective, this is the bump map that we recommended. And you're right, this purple we do not define because those are flexible in terms of how you want to use them. Okay,
thank you.
Thank you. So I think this one, we talk about. This one is just is not much information here. It's just to show an integration example where you have the host from a application logic through adapter optional. You see the dotted line through the transport layer, to the OpenHBI. Then the other side, this is a chiplet specific functions. If you assume this is a multi-function chiplet where you can have a protocol like a PCI chiplet, or even optical, networking, storage, accelerations, compute, crypto, compressions, and those kind of things. You put it there, and then you can map dynamically through the adaptation layers. And then, by the way, if I haven't been clear enough, it's 32 D word per instance. So you will have a 32 such D word, which give you again about 10 terabit total. So that's why we anticipate for such a high end or high bandwidth capabilities, we allow the multiple protocol use cases to be mappable at the same time. Very few things can utilize all the bandwidth at once. Even the Gen 6x16 would be 1 terabit per directions and use 2 terabit only, out of the available 10 terabits. So. Okay, this one I think I already go through it. So just to stress that we allow typically is the anchor to chiplet. Someone asked earlier about, can you have a multiple, this, and then absolutely, we can have a multi C2C anchor to chiplet use cases like this diagram in the middle. And then of course, this is not usual, but then we allows a chiplet to chiplet if you want to say, I want to scale. For whatever reason. For the same concept, if this chiplet is a CPU, you know that lots of people do CPU to CPU like this, and then and you can build larger things like this. Depending on your architecture, from our perspective, we only give you a transport and the convenience of orientation independent routing. So with the lane repair capabilities, and all this will be on the interposer, at least for this generations. And so this is limited in size. By that. So, okay, so the last slide I have is, sorry, it actually took longer than I expected. We have the 0.5 published last December. When I said published, I mean the inside of work groups. The 0.7 is coming. We are targeting June timeframe. And then the 1.0 is slightly delayed to the third quarter, fourth quarter this year. So a key summary again is that we leverage proven widely adopted HBM as foundation. We are very focused to target on the high terabit low latency applications. We are architected. We're not trying to restrict and put a lot of constraint. We architected to ease the protocol mapping. But when I said the cross vendor interoperability, those are down the road. With more well-defined so that we allow but we don't have compliance. I mean, just like most other spec, I don't believe the C2C spec will have the compliance, because it is very difficult to constrain that. Orientation independent, this is very important to enable all the use cases with full lane repair capabilities. We allow implementation specific to we harvest bitfront for HBM3 memory if you want to do Dumo. Optionally configurable the TX and the RX personality at boot time or even at runtime. I think the cloud hyperscalers may welcome these features. Finally is the figure of merit. We don't stop at the 2.29. We are planning for the enhanced one in the next generation. So that's it. Thank you very much. Any questions?
Ken, a very quick one. Is there a version of OpenHBI that is less performance but cheaper, like organic substrate or something? Are you working on anything like this?
Great questions. And then I think I kind of alluded to earlier, and I said at least for this generation, we focus on the high bandwidth, I mean the high terabit per second, and focus on the interposer. It has been discussed, but let me just not answer directly at this time, but I would answer as we are discussing, and then has been in our radar. But I think that it is important for us to focus to ensure that the interposer-based design to be successful first, and then before defocusing ourselves. But from a technology perspective, the interposer is like a million times harder to deal with than the organic substrate. So once we get a good hold of the interposer, then the doing the offsuit, I would call the derivative spec to address the organic is relatively easy, or less effort, I would say, not easy, but less effort. But the IO will be different though, depending on what is the target performance. If you want to take the same IO electrical and want to drive to the organic, it will be very different. But if we set everything remains the same from a characteristic and capabilities and features, like the repair, the orientation independent, and all those things, but just change the IO, that is also within the radar of considerations. But if you don't mind, I won't answer straight right at this point.
Sure.
Question, you actually reconfigured the RX as TX and TX as RX, right? So what is the
Yes.
overhead in doing that in terms of power and area?
Okay, so I think you're referring to this minor point. I put it here. Well, depending on how we look at the optionality in the actual specification, we actually recommend the anchor side, the anchor being a more capable side, right? The chiplet, if you look at the anchor, which is a larger piece here, the chiplet will be one of the chiplet that connects to the anchor. For example, we recommended the anchor to have a configurable TX and RX because they are larger. They are, have to talk to different kind of chiplet. But on the chiplet side, if they know what their function is, what their flexibility is, what their configuration is, they can bound themselves, and then they can even have a mix of configurable or non-configurable D-word. By having a fixed personality, you basically saving your I/O. You reduce some capacitance. You reduce some the I/O area. So those we cannot quantify because those are design specific. But I think at least from a qualitative perspective, you can get some area gain. But they are I/O bounded. I mean the micro bump bounded anyway. But then you can potentially save some power because your capacitance will be slightly lower if you are either TX only or RX only. Did I answer your questions?
Yeah, I understand. So the anchor chiplet is something like kind of interposer between the chiplets. Is it like translator between the chiplets?
Yes, you can call that. Yeah.
Okay. And other quick question that you have a depth, right? At least I see 6 level of depth of bumps. And how many layers does it take to route? And how many between bumps? How many traces do you route?
Okay, good questions. So so here we not only 6, but we actually, to be totally honest, this one actually is a 4 deep structure. So you will see a 4 such a depth structure. So if you're strictly looking, you will have 24 deep sharing a 55 micron. If this one is the 110, but if it is 55, like I showed earlier, then it will be 3 times 4, which is 12. So at that, we, depending on your space and the width of your interposer, whether it is fan out or silicon interposer, those are technology specific, and I cannot directly comment who and then the rules, but I will be answering either 2 to 3 layers of the routing resources are needed.
Okay, I mean the 4 depth you can route in 2-3 layers.
2 to 3, yes, depending on the of your space and the width. And also some people said I want to have the best SI they can get, and then they may even choose to have some ground shielding, and that will be substantially increasing your routing resource requirements. So that's when you need to do more than 2 layers. But in some cases, and I cannot comment on all the packaging technologies, 2 layers will be the minimum. We cannot do 1 for sure because the wiring density is pretty high here. I remember our calculation is about 270-ish, depending on your Y pitch. At the 55, I believe it's about 270-ish. So.
Okay, thank you.
Thank you. Good question.
Hey, Kenneth.
Yes.
Hey, first off, thanks for making the time. I know you had to move your schedule for this, so thank you.
Thank you very much.
Um,
So, any more questions?
Every once in a while I get a couple of inquiries about whether someone can join OpenHBI. Is it too late? And B, if it's not, what do people need to do?
Oh, okay. Well, the OpenHBI membership, I think, Bappi, you can answer the question probably better than I am, but because it is a closed work group, there are certain OCP rules that we need to follow. And not only does the prerequisite that we talked about earlier, we actually need to have all the existing members to agree to admit the new members, because after all, they are related to some of the IP already contributed. So one thing that we want to avoid is to, some people join the group and just sit there. Okay. By signing the contribution license agreement, we expect everyone in the members to be active contributors, and luckily we have. And the other thing is that we don't want people to come in and talk and then with no keen use cases or active interest, but then they just want to come in to kick tires to learn what it is. And then the other thing is that at the end, we also need everyone to sign a final spec agreement to agree that everything's in this spec, including the IP that is either they contributed or not contributed, would be granted to the public. Meaning that when OCP release as a public spec, they will have to grant to the world, right? And the members have to be agreeing to the FSA terms even before they sign the CLA. So all this, we have to go through all these processes, and all the members today understand this part. So we just want to be very sensitive, so all the existing members who already executed the CLA need to unanimously admit new members, whether they have the real interest, contribution, and the expertise that we are looking for, those kind of things. And of course, we won't say we won't admit new members, but we are very careful. And Archana also give us the guidance that we don't need a very super big group, because ultimately we just want to have a very focused specification that meet the people's uses. And so whoever really is driving this from their what do you call, from an industry leadership and the vision perspective, the use cases actually would be much better to drive the definition instead of just random ideas. Even if people have some experience, but if they don't have a real use cases that is driving that, it's very hard for someone to understand the true trade-off and challenges. So given that, we still welcome, but the spec is already at around 0.7. So if people believe that they are still have new things to contribute, then please come email me. My email
kind
is
of
hello.
It's cross noise. Hang on, I'll fix it. Keep going.
Okay. Yeah. Basically, I already completed. So my email is kma@xilinx.com. KMA, kind of ma, like kind of ma, but KMA @xilinx.com. If you are interested, you can email me. But then I will send you a small package, like I mentioned earlier, the CLA, the FSA, some of the logistics things, and you guys can consider. But we're already at 0.7. The 0.7 we will publish internally for review at June timeframe. So we are hoping that 3Q, 4Q, we already will have the 1.0. So what I would recommend is, if you're interested in the spec itself, just a couple more months. You don't have to go through the hoops to all these CLAs, FSA stuff. But if you think that you want to be engaged through the next generation as well, then yeah, welcome. Please come email me.
Now, if they can't join the OpenHBI, then the only opportunity to get a good look at that spec is when it pops out by the end of the year, right? There's no intermediate public document you're planning on producing. I'm asking, not recommending.
Correct. You're absolutely right.
Okay.
Yep.
And can somebody ask for if there's sufficient interest, can the group be motivated to produce an intermediate report out, or you don't think that's likely?
Well, whatever I do today is I consider as the intermediate report out, and this the verbal information is already addressing some of the very good questions that I asked. And those are, I would say, some of them may be in the borderlines sensitive information that we usually don't disclose outside of the group. But I mean, what the heck? I mean, so we are under the same ODSA group, so we are sharing as much as we can. So.
Got it. Okay.
Okay, maybe last clarification. How much that is more than what you presented typically? I mean,
I'm sorry, can you ask the question again?
Like for those people who don't have a look at, the closed spec, I'm saying how much more information, if you like, there is more than that you presented today?
Oh, so we have a structure or construct we call the CCT, configuration and test. So that's where some of the test experts come into play. And then we have the config interface definitions, but those are relatively the high level. We have the super detailed bit reordering and those features, and they are very, very detailedly defined in the spec. Some additional lane repair, some of the trainings, clocking, and details in the framing, details in this mode, how to use all these signals in different modes. How do we do the clock repair, like I mentioned before, and those kind of things. So the spec is have lots of next level details of everything that I talk about today, but everything that I talk about today covers just about all aspects except the config and test structure construct that I mentioned.
Okay, thank you.
Thank you.
Quick question on the config and test you mentioned. Since your RX and TX are configurable, how do you support internal loopback, or how do you test the IP by itself?
When you talk about the internal loopback, you're talking about the wafer level or after you packaged?
The wafer level.
That part I cannot answer you because that belongs to some of this CCT stuff, which I kind of purposely do not put it here. Those are the construct that we cannot share at this point. Sorry.
Okay.
Yeah, but enough to say that we fully support the wafer level testing. So as part of the spec recommendations, and then we have details about what kind of signal, propad, and those kind of things defined.
And what about the package level testing? You support that too?
One more time.
What about the package level testing?
We allowed, we have provision for signals for vendor specific testing. We don't define things like, if you look at HBM where they have the IEEE 1500, that you can have some well-defined commands. No, we don't, and they are not for testing, right? They're for enabling, and then we have our own config interface to initialize. But from a post-package testing, well, I'm again going into a little bit more. We allows a mode that to give you the signals to do it, but cannot talk about the details yet. Sorry.
I hate to cut this off, but we're about a minute past, so thank you, Kenneth.
Oh, thank you very much. Thank you very much. Good questions.